Okay, a very big welcome to another video on physics in St. Andrews, and today we will be talking about waves. Okay, so this is going to be a very short video because the topic on waves is just a kind of introduction to what a wave is before we go on to study specific waves like sound wave. Yeah, so for today you have to know that a wave is a vibration that carries energy away from the wave source. So please write down, fill in your notes as you follow along. It is a vibration that carries energy away. Okay, so anything that vibrates will create waves. So anything that doesn't vibrate, very likely there's not going to be any sort of waves to it. Okay. Next term that you have to know is wave front. So what is a wave front? A wave front is an imaginary, and this is a key word. You can't write it is a line joining all the points of the wave that are in the same phase. You have to say that it is an imaginary line because it doesn't really exist. Okay, you can see it, but it doesn't really exist in most parts of the waves, but it's there, and it's there to help us do some basic calculations, as we'll see later. Okay. Next, you have to learn what are the different parts of the wave. So, first of all, know that the top of the wave is called the crest. Okay, it's called the crest. And the bottom of the waves, the very bottom of the waves, they are called troughs. Okay, and you should know also that the height of the wave, from the rest position all the way to the top of the wave, the height of the wave, now this is called the amplitude. Yeah, amplitude. Okay, now you can measure the amplitude from the rest position to the maximum height, or the rest position to its minimum height. It should be the same in most cases. Okay. Now there's one more term, one complete cycle, one whole wave. Usually, what we do is that we measure it from a crest to the nearest crest. I say again, from the crest to the next nearest crest. That is what we call a wavelength. Okay, so get to know these parts, and because I'll be using these terms a lot. Now, one wavelength can also be made up of one whole positive part of the wave, followed by one whole negative part of the wave. Yeah. Okay, so there are actually many different types of wave shapes, but don't worry, for your standard it will be a very uniform sort of shape. Yeah, there's nothing crazy going to be given to you. All right, so now that you kind of have a visual idea of what the wave looks like, now it's time to get technical, and yeah, let's find out the exact definition of some of these terms. Okay, so A, it is the amplitude. All right, capital A stands for amplitude. And basically the amplitude, remember how high it is or how low it is, will tell you how much energy the wave has. So the bigger the amplitude, the bigger the wave is, the more energy it has. And that kind of makes sense, doesn't it? Next, this funny symbol here, this is called the wavelength. Okay, and this symbol here stands for lambda. And how you write lambda is a backslash line like this, followed by a line something like that, ish. Okay, just get the shape ish, and you should be good. So the symbol is called lambda, and lambda stands for wavelength. Okay, so moving on. F is for frequency. This is a small f. Yeah, frequency, and frequency is the number of complete waves produced per second. Now, needless to say, please go remember all these definitions here. Okay, you have to remember these definitions over here. So, how many waves are produced in 1 second? Well, that gives you the frequency. Okay, so if you got 50 waves produced in 1 second, the frequency is 50 hertz. So this is the unit for frequency. Okay, capital H, small z, and this stands for hertz. So this is the unit for frequency, hertz. Capital T stands for period. So period is the inverse of frequency. It's the time taken to produce one complete wave. And the SI unit for period is second. So what I mean by it is an inverse of frequency. There's a formula which you will see later on down here. 1 over frequency gives me the period. And it kind of makes sense, right? If 1 second has how many waves, if you inverse that, well, that would mean that that's the time taken for one wave. Okay? Go think about that. I can see like the clock symbol counting down as you kind of think about that. But don't worry, you'll get it. And finally, we need to talk about the velocity. Okay, the speed of the wave, the velocity. The wave velocity. Okay, so go remember is the distance traveled by a wave in 1 second. And the wave velocity unit, meters per second, is exactly as chapter 2 when we studied about speed and velocity. Is exactly the same, except that now we are talking about how fast a wave travels. Okay, the distance traveled by a wave in 1 second. Next, some equations. Okay, so you have to remember how to use this equation, this equation, this equation, and you have to know, besides remembering, you have to know how to apply them. There are some examples later on down below, but for now, go remember these 3 formulas. If you have to, pause the video here, go memorize the formulas by heart. Go memorize them by heart right now. And once you're sure that you kind of remember the formulas well enough, then play the video. Now, we've already gone through these 3 symbols, what these 3 symbols stand for. You have to, right now, kind of say it before I say it, okay? So, try your best. V stands for velocity. I hope you got that right. And the units for velocity, say it, meters per second. Now, this funny symbol here. The name of this symbol is called lambda. Hope you got that right. And lambda stands for, say it, wavelength. Okay? And the SI unit for wavelength, well, it is a length after all. It is measured in meters. Capital T stands for period. Hope you got that right. And the SI unit for period is seconds. Okay, so now that hopefully you have kind of remembered the 3 formulae, V equals to lambda over T. Okay, V equals to lambda over T. F equals to 1 over T. And V equals to F lambda. We are now ready to solve some questions. Okay, so let's take a look at question A. Calculate the period of the wave whose frequency is 600 hertz. Okay, so the unknown is period. What's given is the frequency. Okay, so T and F. Now I want to ask myself, which formula involves these 2, T and F? So if you remember the formulas correctly, the formula that I'm thinking of is T equals to 1 over F. Okay? This one. And you'll be going, whoa, hang on, that's not right. You gave me F equals to 1 over T. But if you do a little bit of maths wizardry, you kind of pay attention to what your maths teacher say, and you kind of do a little bit of massaging, you'll find that T equals to 1 over F as well. That's very simple maths. Okay? So if you're wondering, oh, what? You mean I got to remember another formula? Actually, not quite, because this formula, you can easily derive this formula. It's very simple. Okay, so just remember this one and you get the other. Piece of cake. So now we've written the formula down. Let's put in the values. So 1 over 600 hertz. Now, do we leave our answer over here as a fraction? Do we leave it as a fraction? In 3, 2, 1. The answer is no, we don't. Okay? So what we have to do is press your calculator, which is what I am doing now. And I find that I get the answer of 0.00167. This is to 3 significant figures. And the SI unit for period is seconds. Okay, so that's your final answer, 0.00167 seconds. Remember, never leave your answer as a fraction. Always leave it in terms of a decimal place. And if it's not told to you, leave your final answer to 3SF. Next, let's look at part B. Right, let's look at part B. What is the wavelength? Now we're talking about wavelength, lambda, whose period t is such a number and traveling at speed v of 800 meters per second. Okay, so let's go through the formulas. We have v equals to f lambda. We also have v equals to lambda over period. Now, what they have given is lambda, so we need lambda. They've given the period, which is t, and they've given the speed, which is v. So we are looking at this formula over here. Okay? So let's fill in the numbers here. So remember, we're looking at this formula. Write this formula down. Start filling in the knowns, which in this case is 800 speed. Lambda is the unknown. And the period is 0.00125. Okay. Press your trusty calculator, which I am doing right now. And I get the answer of 1. Okay. Don't forget the units. Units for wavelength is measured in meters. So you get 1 meter. Okay. Now, I have done part A and B for you. And right now, I want you to try, just try doing part C and D on your own. Okay? So pause the video here. Do part C and part D on your own right now. And if you've completed and you think that you're confident of your answer, press play again. Okay, so I hope you did try it yourself and not just carry on watching. So let's look at how we solve question C here. Okay, so frequency is what's the unknown, wavelength is given, speed is given. Okay, so the formula that I'm thinking of is V equals to F lambda. V is 450. Frequency is the unknown. Lambda is 0.2 meters. Yeah. So let me whip out my calculator. Frequency is 450 over 0.2, and this gives me 2,250 hertz. Okay, remember, frequency is measured in hertz. 2250 hertz. Okay, let's go on to part D. Frequency is given now. Wavelength is given now. How long? They're talking about the time. Does it take for the waves to travel 2,500 meters? So, first of all, let's find out what the speed is. Okay, I'm looking at these two information first, the frequency and the wavelength. And having this information, I can first of all calculate what the speed of the wave, because frequency is 1500, wavelength is 0.16, and 1500 times 0.16, and this gives me an answer of 240 meters per second. This is a two-part question, so to kind of denote the second part, I'm going to change the ink color. Second part, I'm going to apply the usual formula DST. The time taken is distance over speed. The distance is 2500. The speed of the wave is 240. Let's press the calculator, and I will get an answer of 10.4 meters, seconds. We're talking about time here. So the time taken for the wave to travel 2,500 meters is 10.4 seconds. Okay, so this is a two-part question. There are some questions where you do have to find an unknown before you find the final answer. This is one such question. Okay, next, part E. State the number of complete waves in the diagram. So follow me as I go count waves. Okay, so this is one, because we are talking about one complete crest, one complete trough. This is one wave, two wave, and this, I don't have the full wave, so this is half of the wave. So one more time, 1, 2 and a half wave. So I know I've got 2.5 waves over here. State the amplitude. Now I'm going to zoom in here. This is not the amplitude. Okay, 0.2 meters is not the amplitude, because 0.2 meters is the distance from the crest to the trough. Now if you remember, the amplitude is only measured from the position of rest to the crest or the trough. So in this case, what you have to do is you have to take, let's get rid of that technical error. In this case, what you have to do is you have to take 0.2 divided by half. Okay, and you'll find out that the answer is 0.1 meters. So that is the amplitude, 0.1 meters. And calculate the wavelength. So the whole shebang, the whole diagram here is 1.5 meters, and we found out there's 2.5 waves here. So 2.5 waves is 1.5 meters. Therefore, to find the wavelength, the length of one wave, I have to take 1.5 meters divided by 2.5 waves, and I'll get the answer of 0.6 meters. Okay, quite simple. These are very, very simple questions that you might be encountering in your tests and exams, so you have to get used to this. All right. Lastly, the types of waves. Now, in the course of your studies, you'll be learning that there are two types of waves. The first type is called a transverse wave. Now, what is a transverse wave? It's a wave whereby the well, let's write that down for you. A wave where the vibration of particles is perpendicular to the direction of wave travel. Okay, and some examples of transverse waves, you have water waves, you've got all the the parts of the EM spectrum, they're all transverse waves. So you can talk about radio waves, you can talk about infrared waves, you can talk about light waves. So all of these, they are all transverse waves. Okay. Now, if you manage to remember what a transverse wave is, then you'll be able to remember what a longitudinal wave is, because it's going to be exactly the same. Watch. A wave where the vibration, if you notice, word for word is the same, of particles. Of particles is. Now, this is where it differs. Okay? This is where the word perpendicular, you have to change it to parallel. Okay, so that's the only difference in both the definitions. Okay, so one is perpendicular, transverse. The other is parallel. Is parallel to the direction of wave travel. Okay, so please go remember these two definitions. Go remember them. I will kind of explain to you what a transverse wave is and what a longitudinal wave is. I think a video would serve very nicely, and we'll watch that video in class. Okay, an example of a longitudinal wave is sound wave. Okay, sound is the only longitudinal wave that you'll learn. Okay? And that is it. So I've kind of included in this fun fact over here. You don't have to know this. You just have to know that when the water is very deep, actually, the speed of the wave and the wavelength is actually very high. But as you get to a shallower region, just think of this as the beach, right? In the deep sea, the waves are actually very fast and the wavelength is quite large. But as it gets closer to the shore, the speed decreases and the wavelength decreases. So this is just a fun fact for you to know. Not in your syllabus, well, unless you are studying pure physics, then you have to know this. But otherwise, that's it. That's it for the short video on waves. If you have any questions, please ask me in class, or you can email me. Okay? Other than that, that's it. I'll see you in class. We'll go through some work then. Okay, goodbye.